We start. So let's see an example of a learning problem. This is a toy problem, but has interesting features. So the problem is called Bongard, from the name of a Russian scientist, and the examples are pictures, and the task is to discriminate positive pictures from negative pictures. And the pictures are very simple. They contain shapes that can have properties such as being small, large, pointing down, pointing up, and they are in different relationship between them, such as inside one picture, one shape is inside another, one shade is above another, and so on. So you can generate pictures randomly according to a rule that separates positive from negative pictures, and then the task is to learn the rules that you use for generating the pictures. So in this case, each make example describes a single picture, okay? And for example, for EMBLEM, you can provide the description of the mega examples enclosed in begin model and end model. This is a mega interpretation. In this case, you have a single example per mega interpretation. The example is this one. Pos is the predicate you want to predict, okay? And it has no argument because it is referred to the whole mega interpretation. And this interpretation describes a picture where you have a triangle which has identifier O5. O5 is a triangle pointing up. O4 is a square. O4 is inside of 5, so the square is inside the triangle. O3 is a circle, and so on. Okay. In general, you may have more than one example for mega interpretation. In this case, if you have more than one example, the atom should have an argument for distinguish the various examples. And then you have a negative example, which is a picture where the target predicate is enclosed in a neg predicate, stating that in this case, pos should be false, so it's a negative example. And then suppose you have this theory, which says that the picture is positive, it contains a circle A, and something is inside A. B is inside A, where anything can be inside A. Or a picture is positive with probability 0.5 if it contains a circle and a triangle. So if you are given this theory, you want to tune the parameters. Again, as for Prism, the interpretation do not record the truth value of ground atoms, do not record the truth value of random variables, but only of ground atoms. So you don't know for each probabilistic choice, for each probabilistic clause which head is selected. So you have unseen data. You can't use relative frequency. You have to use expectation maximization, as for Prism. So in EMBLEM, you perform expectation maximization, and you use BDDs for computing the expectation. The BDDs are built for explaining the example. So the examples are queries which are explained by building a BDD that represents the set of its explanation. The expectation are computed over the BDDs. The BDD is the binary decision diagram, are used to encode, are based on Boolean variables, variables with two values, 0 or 1. While in LPAD, a head can have more than two atoms. In this case, you have to encode choices with more than two alternatives using Boolean variables, and you can use various encodings. EMBLEM uses this one, which is also used by Problog. So you have each grounding theta j of a closed CI. Theta j is a substitution that replaces variable with constant. So you have a closed CI of your program. You have to generate the choices. You have to generate the grounding. So you pick a substitution grounding CI. So you have a ground close CI theta j, and to each ground close of this form, you have a random variable that has n values if n are the head atoms of CI. So you encode a random variable with n values with n minus 1 Boolean variables. So equation xij equal to k for k equal to 1 or n minus 1 is represented by the negation of all the Boolean variable up to k minus 1 plus the Boolean variable k, okay? And for the last value, if xij is equal to n, you represent with the negation of all the Boolean variables. If you compute the parameters of this Boolean variable using this formula, the representation of multi-valued random variable with this Boolean variable is equivalent. So you can obtain the same result for the probability of queries. So to compute the expected count, you have to consider all the grounding substitution for a close. Let's call GI the set of grounding substitution of closed CI. Okay, so you have a set of random variables, Boolean xij, the variable for closed CI, grounding substitution j, a value k, where k is from 1 to ni minus 1. So for each of these variables, you have to compute the expected count. Let's see an example of a program and the corresponding random variables. This is an LPAD where the first clause has 2 atoms in the head, but the probability do not sum up to 1. They sum to 0.9. So there is an extra atom null that is left implicit, whose probability is 0.1. So this program models a very simple model of the development of an epidemic or a pandemic. The first clause states that if there is a person X who has the flu and the climate is cold, there is probability 0.6 of the development of an epidemic and probability 0.3 of the development of a pandemic, or probability 0.1 that nothing happens. Then you know that the climate is cold with probability 0.7 and David and Robert have the flu. So you have 2 constants. You have a clause with a variable. So this clause generates 2 ground clauses, one with X replaced with David and one with X replaced with Robert. So clause C1 has 2 groundings, okay? Each grounding has 3 atoms in the head. So you have a multi-valued random variable. So you have to encode it with Boolean variables. You use n minus 1, so 3 minus 1, 2 Boolean variables. So for the first grounding, you have Boolean variables x111, x112, and for the second clause, you have x121 and x122. Clause C2 has a single grounding because it has no variables, and you have a single Boolean variable x211. So if we ask the query epidemic, in this program is true if the first head is selected for the first grounding of the first clause. So if the first head is selected and for variable x211 the first head so-called is selected, then the query is true. Otherwise, if for the first grounding of the first clause, the first head is not selected, you have to check the second grounding of the first clause. If the first head is selected, you check for cold. If it's selected, the query is true. Otherwise, the query is false. So this is a binary decision diagram. Every level is associated to a Boolean random variable, and this BDD represents the truth of the query epidemic. So epidemic is true if for the first grounding or the first clause I select the first head, and for the only grounding of the second clause I select the first head, or if the first grounding of the first clause I don't select the first head, but I select it for the second grounding of the first clause, then the query is true. Note that some variables are absent from this diagram because they don't influence the truth of the query. So x112 is absent here because it does not influence the truth of the query. So you have to compute the expectation, you have to compute the expected count for all the Boolean random variables, and you have to sum this expected count for all the groundings. Why? Because all the groundings of the clause share the same parameters. So when you compute the expected count, you must sum this conditional probability for all grounding of clause CI, because the parameter for clause CI is shared by all the grounding. So you compute the expected value of the count for clause I, Boolean variable k, and x is either 0 or 1. So Boolean variable k being either true or false, and the expected count is given by this conditional probability. The conditional probability of Boolean variable xij equal to x, equal to 0 or 1. So you have two expected counts for each Boolean variable, one with x equal to 0 and one with x equal to 1. And then in the maximization phase, you could sum up the values for all the examples, and you compute the new value of the Boolean, of the parameters of the Boolean random variables, from which you can compute the parameters of the original multi-valued random variables. Okay, so by the definition of conditional probability, this conditional probability is given by this fraction. Okay, and now, as Luke was showing you yesterday, BDDs are built by merging nodes and deleting nodes. Okay, suppose you consider the program before where you apply only the merge rule and not the delete rule. The merge rule is used when the BDD has two subgraphs that are identical. In that case, you remove one of the two and you make all the nodes that pointed to the deleted one to point to the remaining one. The merge rule instead is used to remove a node where both edges, outgoing edges, point to the same node. So in this case, for example, this node n prime 2 has both children pointing to n3. This means that for any values of this variable, you will go from n1 to n3. Okay, so this node is not needed. In fact, is absent from the BDD here. There is no node for x12 here. Okay, and similarly here for n prime 3 has both edges going to 0, so it's not relevant. In fact, here there is no node for x21 on this branch. So consider this BDD. Okay, the probability of an example is the sum of the probability of all the paths that go from the root to a one leaf. Okay. So, since we want to compute a joint probability, and we want the Boolean variable xij being either 0 or 1, we can do it by considering only the paths that go through the x child, where x is at 0 or 1, of a node n associated to xijk. So, this joint probability is given by the sum for all the nodes of the level of this random variable. So for all the nodes associated to random variable xijk, you compute this formula, which is Fn is the forward probability or the probability mass of the path from the root to node n. B of n is the backward probability, the probability mass of the path from n to the one leaf. So you multiply the forward probability of n times the backward probability of the 0 or 1 child of n times the parameter of the Boolean random variable. This is the sum of the probability of path that pass through a node associated to variable xijk and go through a next child, a 0 or 1 child. Okay, this is requires a little bit of thinking, but you can, if you think a little bit about it, you can understand it. So we call this quantity EXN, meaning the expected value for value x. Okay. So in case you obtain a BDD where you apply also the deletion rule, so you apply both the merge rule and the delete rule, this formula applies only for BDDs like this. In general, when a BDD is like this, you have to consider also deleted paths. Okay, because the deleted path can contribute to this joint probability. I won't go into details, but deleted path must be taken into account. So, given this formula, we need to compute the forward probability and the backward probability for every node. The backward probability, the probability of mass of every path from a node to a one leaf, is the probability that is computed for answering the query. So B of root is the probability of the example. Okay, this probability can be computed bottom up with this algorithm. So you call this procedure with a node, and if the node is terminal, you return the value of the node, either 0 or 1, if the node is a leaf. Otherwise, you call yourself recursively on the 0 child and the 1 child of the node. You get these backward probabilities of the two children of node, and then you compute the probability of the backward probability of node by multiplying the backward probability of the child node times 1 minus the probability of this variable plus the probability of the one child times the probability of the node. This is the dynamic programming algorithm that was used in Problem 1, that is used in CPLE to compute the probability of queries. Here there are other commands that are used for parameter learning, but backward probability can be computed in this way. So by visiting the BDD bottom up. Instead, forward probability can be computed by visiting the BDD top down. So you first compute the forward probability of the root, which is 1, because the sum of the probability of paths from the root to itself is 1. Then you initialize the forward probability of every node to 0, and then you scan the BDD level by level, starting from the first level, and for all nodes of the level, you compute the forward probability you update the forward probability of its children. So you pick a node from the level L, let xijk be the variable associated to the node, and if the 0 child is not a terminal, you update its forward probability by summing the forward probability of the node times the parameter of the variable, which is 1 minus pi ik, since this is the 0 child. and you add the child to the list of node to be visited. Otherwise, you update the forward probability, adding the forward probability of node times the probability of the random variable. So in the backward phase, besides computing backward probability, you compute also the expectation, and you update the expected count for each rule that are used afterwards for the maximization phase. Let's see an example. Consider the BDD seen before. Okay, let's compute the forward probability. So we start with the forward probability of the root, which is 1. We consider this node node n1, and we update the probability, the forward probability of its children. The forward probability of the 0 child is the forward probability of the parent times the probability of the variable associated to n1 being false, which is 0,4. So the forward probability of n2 is 0,4. We can compute the forward probability of n3, which is 0,6 times 1, which is 0. Okay, 0,6 times 1 plus the forward probability of node n2, which is 0.4, times the probability of the random variable x1 to 1, which is 0.6. So 0.4 times 0.6 is 24, plus 0.6 is 0.84. This is the forward probability of node n3. And this is the end, because there remain only leaf nodes. Then let's compute the backward probability. The backward probability is computed bottom up. Let's start with node n3. The backward probability is the sum of the probability of the children multiplied by the probability of the random variable. So here you have 0.7 times 1 plus 0.3 times 0, which makes it 0.7. Then you compute the backward probability of node n2, which is 0.4 times 0, which is 0, plus 0.6 times 0.7, which is 42. Okay, let's compute the backward probability of node n1. You multiply 0.4 times 0.42 and 0.6 times 0.7, and you get 0.588. This is the probability of epidemic in the example above. And we have also computed the backward and forward probability, and we can compute the expectation and expected count. So this is how EMBLEM works. EMBLEM must also take into account deleted paths. So here you have this sentence, take into account deleted paths. I won't go into detail because they are rather technical, but it is necessary to take into account also deleted paths. Okay, so in Problog, there was a system called LeProblog, which used to perform parameter learning using gradient descent. LeProblog minimizes the mean squared error of the example. Different from EMBLEM, in LeProblog, the examples are associated with a probability. So each example is associated with a probability. The learning problem of EMBLEM is equivalent to this one, where the probability are 1 for positive example and 0 for negative example. Here you can have also intermediate values. So you can have an example true with probability 0.7, and the task of LeProblog is to minimize the mean squared error of the probability of the example computed according to the problem with the probability of the example given in the training set. LeProblog performs gradient descent, so updates the parameter using gradient descent. So it is necessary to compute the partial derivatives of the mean squared error with respect to each parameter. So if you derive the mean squared error, you obtain this formula, and you have to compute the probability of the example with respect to each parameter. And LeProblog does it using the BDDs, again, with a dynamic programming algorithm that traverses the BDD twice, once bottom-up and once top-down. Okay, I won't go into the details of the computation of the gradient. There is one catch, which is when you perform gradient descent, you repeatedly update the parameters in the opposite direction of the gradient. The problem is that the parameters in Problog are constrained in being between 0 and 1. Okay, so when you update the parameters with gradient descent, you may go out of the 0-1 interval. So to avoid this, we use a reparameterization where the parameters are numbers which give the probability after being applied to the sigmoid. The sigmoid is a formula that has a domain of the whole real line, and the codomain is 0, 1. So in this case, if you use as parameters the argument of a sigma function, the parameters can have no limits, so you can update them as you like. You have no problems of falling out the 0, 1 interval, so this makes learning much easier, and you just have to correct the derivative. Problog 2, the latest version of Problog, includes a version of learning from interpretation Problog, LFI Problog, that learns from partial interpretation, which are couples that indicate both the true and the false atoms in the example. So you can associate each partial interpretation with a query, which is the conjunction of the true atom in the partial interpretation and the negation of the false atom in the partial interpretation. And you want to maximize the likelihood, so you want to find the value of the parameters that maximize the probability of the example, that is the probability of each query built for the partial interpretation. So you want to, this is the likelihood of the example, you want to maximize the likelihood. LFI Problog, as Problog 2, uses DDLNF circuit, so the composable deterministic negation normal form circuit, which are similar to BDDs, but are less constrained as with respect to BDD. They offer some advantages in terms of compactness of the circuit. So, if you consider this example, which is a simple example of an alarm domain, it's very similar to the alarm Bayesian network that you find in many text-to-tone Bayesian networks. So, there is alarm if there is a burglary, there is an alarm if there is an earthquake, and there is a burglary with probability 0.1, an earthquake with probability 0.2, and you have also a clause that states that X calls if there is an alarm and X if the alarm. If the alarm is defined by this probabilistic clause that says that X is the alarm if there is X is a person with probability 0.7, and we know that Mary and John are persons. Suppose you want to compute the probability of burglary given the evidence that John calls, okay? So if you have this query, this evidence, you build this deterministic decomposable negation normal form, which is a circuit where you have AND nodes and OR nodes, okay? And the leaves are literals of the program, so that can be either positive or negative, okay? So the query burglary given evidence called John is true if you assign value to these leaves, and you evaluate the circuit, and the query is true if the circuit returns 1. In order to perform parameter learning over these circuits, these are transformed by replacing conjunction with multiplication, disjunction with sum, and by splitting leaf nodes into two. One, which is called an indicator variable associated to each literal, indicated with lambda colon, for example, and the other one, which is the parameter, which is the weight of the literal. And then you compute the probability of the query given the evidence by performing weighted model counting with this circuit, which is performed by simply evaluating the circuit bottom up. So you replace conjunction with multiplication, disjunction with summation. You split leaves by adding a child with the lambda, with the indicator variable for the literal, and a child with the parameter. And if you assign values to the indicator variables and you evaluate the circuit bottom up, you obtain the probability of the query. So this circuit represents a Boolean formula that is equivalent to the truth of the query given the evidence. In general, the weighted model count of the formula phi is given by the sum over all the words that satisfy the formula, or the assignment of all the variables that satisfy the formula, and for the weight of each word. The weight of each word is the product of the weight of each literal times the indicator variable of the literal. And this formula can be computed by evaluating circuit. In particular, the probability of the example can be computed by setting all indicator variables to 1, because in this case you get the sum over all the words that satisfy phi of the product of all the literals in the word, and this is exactly the probability of E. So the probability of evidence is obtained by setting all indicator variables to 1. So if you use this formula, replace all indicator variables with 1, you get the probability of the evidence. Now, in order to perform the EM algorithm, we need to compute the conditional probability of the query given evidence for all atoms in a set of atoms. So consider the partial derivative of the function represented by the circuit with respect to one indicator variable, for the indicator variable for the query. If we perform this partial derivative, we see that the indicator variable appears only in this product. So you throw out all the words where lambda q does not appear, and for the other words you remove lambda q. So if you set then all the other indicator variable to 1, you get the probability of the evidence and the query. And this is given by the sum over all words satisfying phi and that also contain the query. So this is the joint probability. So if we compute the derivative of the formula with respect to the indicator variable, we get the joint probability that are needed for the EM algorithm. So we need to compute derivative. And this is done as in PRISM. In PRISM, the outside probability are partial derivatives of the probability of the example given the various parameters of the program. Here again, we need to compute the partial derivatives of the function represented by the D and F with respect to each indicator variable. And this is done with a recursive algorithm, a dynamic programming algorithm. I want to go into detail of the formula. but you simply visit the circuit twice, once bottom up from the leaves to here, okay. Here you visit children before parents, so bottom up, and you compute. Vn is the value of each node. The value is the one that is computed by evaluating the circuit. And then you compute the derivatives, which are indicated with dn for the node. So you visit parents before children, you visit the circuit top down, and you update the derivatives using formula similar to the one of Prism. So, as you can see, the learning algorithm all perform dynamic programming algorithm over a structure that permit the computation of the expectation in a fast way, because considering all explanation is not feasible because there can be an exponential number of them. So Prism uses a very simple algorithm that does not need to perform knowledge compilation as EMBLEM or Problog, because of the assumption of mutual independence of the atom in the body and exclusivity of the disjunction. Okay, so Prism, LeProblog, LFI Problog, EMBLEM all perform similar dynamic programming algorithms. The formulas are slightly different because they use different circuits, different approaches, but the concept is the same. Usually, you need to produce a data structure that you can visit to perform the expectation. So, at this point, we are ready to discuss structured learning. In this case, you are given the same data as for parameter learning. You have a set of interpretation, a set of mega example, and in this case, you want to find both the structure and the parameters that maximize the data, or the log likelihood of the data. One such algorithm is SLIPCOVER that performs a search in the space of theory in two phases. First, it looks for good candidate clauses, performing a beam search in the space of clauses. Then it performs a greedy search in the space of theory by adding the good clauses found in the previous phase one by one to an empty theory and relearning the parameters with EMBLEM. In SLIPCOVER, you have to specify a language bias, which indicates the form of clauses you want to learn, and you may want to learn clauses for more than one target predicate. Okay, so you may want to learn clauses that have more than one predicate in the head. EMBLEM SLIPCOVER performs a beam search in the space of clauses for each predicate that can appear in the head. And the beam search is performed by first generating a set of bottom clauses that are used to bound the search space from below. A bottom clause is a more specific clause that covers an example. So you specify mode declaration. You specify mode declaration for the head and for the body. The mode declaration have a recall number and a predicate mode. The recall number is an integer or an asterisk, and the meaning will be clear in a moment. The predicate mode is a predicate applied to a number of arguments which are of the form mode type, where mode can be either plus, minus, sharp, or minus sharp, and the type is a constant. So, for example, this declaration here indicates that the predicate mem can appear in the body of clauses, and the first argument must be of type number, the second of type list, and plus means that these are input arguments. So when this predicate is called, this argument must be instantiated. Instead, minus indicates an output argument, so when this predicate is called, in the body the argument can be instantiated or not, and the sharp indicates that this predicate can appear in the body with this argument replaced by a constant. So the types are plus, minus, sharp t, or minus sharp t. The difference between the two will be clear in a moment. The argument can contain function symbols. There is no problem. So you have, for example, you may have this second argument, which is a list. So the bottom clause is a ground clause where the example is in the head. In the body, you have a conjunction of atoms that regard the example. Regard in the sense that they have as argument either constant appearing in the example or constant appearing in atoms that in turn have constants appearing in the head. So this set of literals is built by performing a cycle starting from the constants appearing in the example and querying the data with the goals obtained from the mode declaration and adding the constant to the current list of constants and increasing the list of constants that are then used for generating literals of the bottom clause. The difference between sharp t arguments and minus sharp t is that when a predicate has sharp, this predicate is not used in the bottom clause construction phase to retrieve values for this argument, while if you have minus sharp, you can retrieve values for this argument. The meaning is that if you have a predicate like this, equality, okay, and you want to compare an argument of type integer with a constant, if you fill this argument with a value, and you ask and you leave this argument free, and you ask this query, you always get success. While, for example, if the predicate was a comparison predicate, and you would get an error because the second argument would not be instantiated. So some predicates cannot retrieve arguments, constant arguments, some other can, and for this other we use minus sharp. So I don't want to go into the details of the argument, I just want to show you an example. So suppose you have an example E, we state that John is the father of Mary, and you have a background which is the data of on your example, which is listed with this set of facts, and you have a mode declaration where you know that father can appear in the head and has two arguments of type person, both the input, and parent is can appear in the body and has an input argument of type person and an output argument of type person, or now an input argument of type person as second argument and minus sharp as first argument. Male can appear in the body, female can appear in the body as well, but with an argument that is a constant. You can build this bottom clause. So parent John Mary is related to father John Mary because both constants appear in the example. Male John is related to the example because John appears in the constant. Parent Kathy Mary is related to the example because they share Mary. Female Kathy is related to the example because it shares the atom Kathy, which is shared by parent Kathy Mary with the example. Once you have built this bottom clause, it is transformed into a non-ground clause by replacing constant with variables and replacing plus or minus arguments with variables, with the caveat that plus argument must appear as an output variable with the same type in a previous literal. while constant arguments are not replaced by variables. So in this case, we get this bottom clause where Kathy is present as a constant because we had the mode B where we have the sharp here and here. So we build bottom clause. Why bottom clauses are useful? Because this set of literals are used when refining the clause. In the search of the space of clauses, clauses are iteratively refined by adding literals to the body. The literals to be added to the body are taken from the bottom clause. Why? Because this bottom clause surely covers an example, the one for which the bottom clause was built. Therefore, if we add atoms from the bottom clause, we are sure that the refinement covers at least one example. Moreover, you have to specify also, in case you have multiple head predicate, which predicate depend on which other predicate. So in this case, pred 2 can appear in the body of clauses for pred 1. You can also have mode declaration for clauses with more than one atom in the head. They have a specific form because with this declaration you specify head atoms for clauses with a single head. If you want to learn disjunctive clauses, then you can use this other syntax where you have again schemas with the place marker for indicating the type and mode of arguments, and then you have also a conjunction of atom to query for retrieving constant, and also the list of predicates that can appear in the body of clauses with such an head. Basically, SLIPCOVER performs a beam search for each predicate that can appear in the head, and starts with a clause with an empty body with the atom H of the head of the bottom clause. The beam contains couple clause literals, where literals are those of the bottom clause. And at each iteration, the refinements are formed by adding literals to the body. Once you have added the literal, you have to score the refinement, so to evaluate a heuristic function of the refinement, and this is done by performing parameter learning on a theory containing the single clause, and this is done using EMBLEM. EMBLEM returns the updated parameters and the log likelihood of the example, which is used as the score of the clause. All clauses so scored are inserted into a list of good candidate clauses, which has a limited size and is kept in order of log likelihood of heuristic. So at the end of the clause search phase, SLIPCOVER has a set of good candidate clauses that it can use to learn theories, and theories are learned greedily, starting with an empty theory, adding a clause to the theory, relearning the parameters, and if the log likelihood improves, so is higher than before, then the clause is kept in the theory, otherwise it is discarded. And this is performed for every clause in the list of promising clause TC. Then SLIPCOVER considers also background clauses, clauses for predicates for which you don't have example, but you want to use to provide background predicates for the target predicate. So SLIPCOVER treats differently the predicates that you want to predict, that you want to improve on predicting the truth value of atom from the background predicates. The background predicates are learned in block and then added all together to the final theory before parameter learning. Let's see an example of the UW-CSC dataset. You want to learn various predicates advised by, and you have a mode H for advised by, but you have also mode H for disjunctive clauses. This one, for example, specifies that you can allow clauses with advised by and temp advised by in the head of clauses. This one specified disjunctive clause with student and professor in the head, and so on. And then you have also more declaration regarding predicates that can appear in the body, like this one. And an example of a bottom clause for this problem is this one, where you have the advised by atom in the head, and then you have a long list of literals that are generated by variabilizing a bottom clause related to a specific example. This is for the mod H predicate in the case of a single head. This is for the case of more than one head. This is the bottom clause for this type of head. So what happens is that by refining the previous bottom clause, you may get a bottom clause of this form. This is scored by running EMBLEM, which sets the parameter 0.10 and so on. Then the clause is further refined by adding another literal, and EMBLEM is run again to find the updated parameters, which are this one. And no, sorry. Okay, this is an example of a refinement for the second bottom clause. Again, EMBLEM is run again, and new values for the parameters are obtained. When searching for the space of clauses, SLIPCOVER may have found a theory with these two clauses, and we run EMBLEM to evaluate the log likelihood, which has improved. So the score, the last clause is kept, and then we try again to add another clause and perform again parameter learning. Another system that performs structured learning is ProbFoil Plus, which, similarly to LeProblog, consider examples annotated with a probability. So you don't consider only positive and negative example, but you consider probabilistic examples, where the probability can be any values between 0 and 1. And again, similarly to LeProblog, you want to maximize the error, which in this case is absolute error. So it's the sum of the absolute value of the difference between the probability of the example and the annotation of the example. And you're given a background theory, again, and a language bias that specifies the set of allowed clauses. ProbFoil learns clauses of this form: H double colon, X double column H if B, with the X a parameter in 0, 1. However, these clauses must be interpreted in this way: H if B M prob ID and X prob ID. So prob ID is a ground atom that is a probabilistic atom in ProbLog and is true with probability X. And the clause has this ground atom in the body. This is important because this clause is different from an headpad clause of the form H colon X if B, because this headpad clause stands for the union of all the ground rule H if HX if B prime obtained by grounding HX if B. While in this case, so in this case you have a different random variable for each grounding. Here you have a single random variable associated to this probabilistic fact, where ID is an identifier which is ground. So these clauses are simpler than headpad clauses of this form, because for each clause there is a single random variable instead of a random variable for each grounding. ProbFoil Plus generalizes M-foil and foil and performs a covering loop and a closed search loop. In the covering loop, it adds a rule one at a time as the theory, and in the closed search loop, it searches the space of clauses by iteratively refining the body. The covering loop ends when a condition based on a global score function is satisfied, and the closed search loop ends when a local scoring function is satisfied. So the whole algorithm is this one. You perform a cycle where you learn a rule and you evaluate the score of the theory with the rule or without, and if the score improves and the clause is significant, then you keep the clause in the theory and you repeat. Otherwise, you stop and you return the current theory. The function learn rule performs a beam search as well in the space of candidates. So for the set of candidates, until the set of candidates is empty, it generates the new candidates by considering the refinement of a rule from the set of candidates. And for each refinement, we check whether the refinement has to be rejected. The refinement has to be rejected if it's not promising. It adds the refinement to the next set of candidates, and it evaluates the refinement according to a local scoring function. If the local scoring function, the refinement, is better than the current best, then the current best is updated. So let's see the scoring function. The global scoring function is accuracy, which is the sum of the true positive plus the true negative over t, which is the total number of examples. The true positive are the examples which are positive and are correctly classified as positive. The true negative are the examples which are negative and are correctly classified as negative. Instead, the local scoring function is the M estimate of the precision of the theory. The precision is can be interpreted as the accuracy of classifying positive example. So it's given by the true positive over the true positive plus the false positive. The false positive are the examples which are negative but are classified as positive. The M estimate adds a term to the numerator and denominator to smooth the estimate. The problem is that the theory that prob4 learns is probabilistic. So an example may not be only covered or not covered, but may be covered and assign a probability which is different from the one that we have from the data. Okay, so we need to generalize this scoring function for the probabilistic case. So remember that each example is associated with a probability. And each example contributes a part pi to the positive part of the training set, and a part 1 minus pi to the negative part. So the total number of positive examples can be obtained by summing the probability of each example and the negative part by summing 1 minus the probability of each example. So suppose you want to score an hypothesis H. The hypothesis H assign a certain probability to the example. So we call it PHI. Okay. Now we want to compute these quantities. The true positive assigned by the hypothesis H, true negative, false positive. Okay. Consider an example EI, this one. Okay. Okay. We want to compute the contribution of each example to the number of true positive. Let's call it TPHI. Okay, this contribution, if the probability of the example is larger than the probability of the example assigned by the theory, this means that the true positive part will be the whole probability assigned by the hypothesis. Otherwise, if the probability of example is smaller than the probability assigned by the hypothesis is overestimating, so the true positive is just pi. The contribution Fp of example EI to the false positive is PHI minus PI if PI is smaller than PHI, because if the probability of the example is smaller than the probability assigned by the theory, then it means that the difference between the two probabilities is contributes to the false positive part. Otherwise, the contribution to the false positive part is zero because the hypothesis is overestimating the example. This is a little bit tricky to get right, but the thing is that each example does not contribute either 1 or 0 to the false positive and true positive rate. It contributes a number which is between 0 and 1. Now, if we want to compute the local score of a clause X double column C added to theory H, where X is the parameter to be learned, we can express the precision, the M estimate of the precision, in this way as a function of the parameter of the clause. Okay, so we need to find the parameters that maximize the local scoring function. If you want to score a clause, we need to find a value of the parameter for computing the local score, which is the probability of the example, or which is the precision of the clause. So this quantity here, the TPHI, the quantity assigned by the hypothesis H to example I, which is based on the probability of the hypothesis of example I assigned by hypothesis H, depend on the value of the parameter of the clause. So in order to compute the local score, we need to find the parameters. And the parameter in this case can be found in a very simple way, because you don't need to perform knowledge compilation, build BDDs, build the NNF. It is enough to consider that M of X is a piecewise function whose derivative with respect to X is either 0 or different from 0 everywhere in each piece. Therefore, you can compute the value of X that maximizes M of X by considering only the endpoints of the interval. So it's enough to compute this M of X for fixed number of X and pick the best. Moreover, profile prunes refinements in order to make sure that you don't evaluate refinements for nothing. So if a refinement cannot lead to a local score higher than the current best, is rejected. And the same if they cannot lead to a global score higher than the current best. So besides SLIPCOVER and PROFOIL, there is also another system that was developed here in Ferrara that is called SLIPCase, which is basically the same as SLIPCOVER, with the difference that it performs a single search in the space of theory. So it applies theory revision operators. So it performs a bin search where each individual element, each individual state of the search is not a single clause, but a theory. And it revises the theory to produce the refinement to score. And the revision are obtained by adding or removing clauses, or adding or removing literals from the head and from the body. Okay. The problem is that bin search done in this way is not very effective. And so we applied a more refined search, which is Monte Carlo free search, where in Monte Carlo free search, you have a search tree, okay, and you want to decide where to expand. With Monte Carlo free search, you first select a node to expand, and then you perform a Monte Carlo search starting from that node, going down for a fixed number of steps selected at random, and evaluating the state that is reached, then propagating back the evaluation. Because this is obtained by considering this logic theory as a bandit problem. A multi-arm bandit problem is a problem where you have multiple slot machines that you can play, and each has a different probability of winning, and you don't know these probabilities. So the question is how to maximize your gain if you are in front of n slot machine of which you don't know the reward. So what you can do is you can try all of them, because by trying this machine repeatedly, you learn something about their probability of winning. The problem is that what you would like to do is identify the one that has the highest probability of winning and play only that one. The problem is that you don't know which one is it, so you have to make a trade-off between exploitation and exploration. You want to exploit when you find a slot machine that has a good probability of winning, but you also want to explore to see whether there are machines with a higher probability of winning. So this is the same for search. You don't know which of these nodes will give the best hypothesis, okay? So the problem is that of trying the different nodes to see if there is one that leads to better solution. Ideally, you would like to expand only the node that provides the best solution, but you don't know which one is it, so you make a trade-off between exploration, meaning that you explore the node and you perform a local search on it, and exploitation, meaning that you consider the children of the node and you perform search in that neighborhood. So this is implemented in the system Lemur, which is available also online in the CPLint web application. Okay, finally, I would like to discuss another topic, which is a combination of probabilistic logic programming with a form of deep learning. So in this case, we consider the problem of the cost of learning, because learning probabilistic logic program is expensive because during learning you have to perform inference repeatedly. Inference is costly, so learning algorithms are slow. But we can restrict the syntax of the languages so that we get faster inference and see whether we can still obtain good models. Okay, so we have considered a restriction of the language of logic program with annotated disjunction, which is called hierarchical PLP. In this case, you want to compute the probability of a predicate R, okay, a single predicate R. So you want to predict whether atoms of the form R applied to a tuple of term is true or false. Typically, this predicate R is a target predicate in a learning problem, and RT is an example. Okay. So you want to predict this probability using an LPAD that defines the predicate R in terms of other predicates, which are divided into input predicate, which are those that are recorded in the mega interpretation. Think about the professor student in the UWCSC domain, or triangle circle in the Bongard domain. Okay. These are input predicates because they are given, their definition is given in the input mega interpretation. Moreover, the program defined in R can also use hidden predicates, which are predicates which are defined by other clauses. Each rule in this program has a single atom in the head annotated with a probability. And the program is hierarchically defined. So at the highest level of the hierarchy, you have the target predicate R. At the level below, you have the hidden predicates that are used in the body of the rules for the target predicate R, and so on. So each layer contains a set of hidden predicates that are defined in terms of the predicate of the layer immediately below and are used in the layer immediately above. It's an extreme form of program stratification. It's stronger than acyclicity because acyclicity is imposed on the of the atom dependency graph, while this hierarchical constraint is imposed on the predicate dependency graph, and is also stronger than stratification that is imposed on the atom call graph, but it allows recursive clauses, while this restriction does not allow recursive clauses, so it is not Turing complete, but it is often useful for representing knowledge. So the generic form of a clause is this one. So you have a head with a predicate P applied to a tuple of variables, and you have a probabilistic annotation. In the body you have, this is a conjunction of literals for the input predicate that uses variable x and y, so the body can have extra variable with respect to the head. Then you have a conjunction of literals for hidden predicate, and each literal must contain all the all the variables in x and y. So you have clauses divided whose body is divided in two: input predicate and hidden predicate. So the form of program is this one. So you have at the first layer you have rules for R, defined in terms of conjunction of the input predicate plus conjunction of hidden predicate. Then each literal B11 is built over a predicate R11 that is defined by a number of rules, okay? And this predicate R11 can appear only in this literal. It cannot appear in the literals that follow in the body or in the literals in other bodies. So you have a structure like this of the clauses and predicates. You have the target predicate defined by C1, C2, Cn clauses. Each clause C1 has a number of hidden predicates in the body, B11, B1, M1. Each is defined by a set of clauses. And the predicate appearing here does not appear anywhere else. So they have a hierarchy. Let's see an example. This is an example for the UWCSC domain where you are trying to predict advice by. So the target predicate is advice by. So the first clause has the part with the input predicate is this one. So student, professor, project are input predicates. They are defined in the data. They are certain. For each of them, you can check whether it is true or false in the data. And then you have a part with the hidden predicate, which contains a single literal, which mentions all the variables appearing in the clauses, so A, B, and C. Note that this clause, this part of the body, is true if A is a student, B is a professor, and they have a project, C, where they work together. And moreover, R11 ABC is true. This R11 is a hidden predicate, and R11 ABC is defined by this clause, which introduces another variable D, and contains two input predicates, publication. Publication, DAC, means that A is the author of a publication D that was produced in the scope of project C, and B, again, is an author of publication D produced in the scope of project C. The second clause instead has no hidden predicate in the body and states that A is advised by B if A is a student, B is a professor, and A is a teaching assistant in a course C that is taught by B. So in this case, you have a single hidden predicate, and the layer, the program has two layers. One with clause C1 and C2 for the advised by predicate, one for clause C11, one for the hidden predicate R11, of which we don't know the meaning exactly. For the moment, we just give a dummy name. In fact, writing program of this form may not be easy for humans, okay? Because we need to satisfy the constraint that hidden predicates are used in a single clause. So it may be unintuitive for humans, but what we can do is we can devise learning algorithm that learns programs in this form. So hidden predicates may need a form of predicate invention to be learned. For performing inference, we need to generate the grounding. And remember that each ground probabilistic clause is associated to a different random variables. The interesting thing is that this program satisfies some assumptions, which are the independent end assumption, because the various literals for hidden predicates are all independent because this predicate does not appear in any other literal. So we can compute the probability of the body by multiplying the probability of each atom. It does not satisfy the exclusive or assumption because the rules may not be mutually exclusive. But the bodies of rules are mutually independent because all the predicates that appear here do not appear in any other body. So this program satisfy independent and independent OR. So the computation of the probability is simpler than in a general case. So the probability of the body is given by the product of the probability of the individual atom. If the atom is a negative literal, you compute 1 minus the probability of the atom. And the probability of input predicate is 1 if the atom appears in the data, and 0 otherwise. Now we have to compute the probability of atoms that are about the target predicate or hidden predicate. Suppose for atom A we have two clauses that have it in the head, in the grounding. Okay. Since we have to compute the probability of an OR where the two distant are independent. So we can use this operation, which is a probabilistic sum, which computes the probability of a disjunction between two events which are independent. And is 1 minus P times 1 minus Q. Is equivalent to P plus Q minus P times Q. And this is the probability of a disjunction. So the probability of an atom is given by 1 minus the annotation of the atom times the probability of the body times 1 minus the annotation of the second clause times the probability of the second clause. This O plus operator, this probabilistic sum operator, is commutative and associative. If I want to perform an O plus operation among a set of values, we get this formula here. And the interesting part is that the multiplication operator and the O plus operator are respectively the T norm and T conorm of the product fuzzy logic, which are called product T norm and probabilistic sum. So if I respect this restriction in writing the program, I get a program where the values of the probability of the atoms are can be interpreted also as fuzzy values. So in this case, for this program, the fuzz interpretation, the probabilistic interpretation coincide, and I can compute the probability of queries much faster because I don't need to solve the disjoint sum problem. I can just practically compute the probability using this formula. So I can replace predicate with plus or plus and bodies with the times, and I get a arithmetic circuit, then I can evaluate to compute the probability of the query. For our example, suppose there are two projects, PR1 and PR2, where Harry and Ben are involved, okay? And there are two courses where Harry and Ben are involved, okay? And for each project, PR1, there are two publications where Ben and Harry are co-authors. So, clause C1 has two groundings, one for project 1 and one for project 2, where the persons are Harry and Ben. Clause C2 has two groundings, one for clause C1 and one for clause C2, and the clauses for the hidden predicate has four groundings for publication P1, P2, P3, and P4. So we can build this dependency graph for ground clauses that leads to this arithmetic circuit for computing the probability of the query. So, for example, these two clauses have both annotation 0.2, so I have two children here with probability 0.2. I combine them with probabilistic sum, so 1 minus 0.2, which is 0.8, times 1 minus 0.2, which is 0.8, so 1 minus 0.8 times 0.8, so 1 minus 0.64, so which is 36. And the arcs which connect multiplication node to O plus nodes are notated with the probability of the clause. So to perform inference on this program, I can just use an algorithm for obtaining the grounding, like PITA, which is a probabilistic inference algorithm that we have developed here in Ferrara. So you can compute. With PITA, you can build the ground circuit, and then you can simply evaluate the circuit to get the probability of the query. Then you can perform parameter learning, and you can do it with EM or with gradient descent. And we have developed algorithm for both. And so we first transform the circuit into this circuit where we highlight the fact that some parameters are shared, so they are the same for various clauses. And then from this circuit we can perform gradient descent or EM. And we have obtained the formulas for, this is the formula for gradient descent. Gradient descent is obtained by evaluating the circuit bottom up and top down, so forward and backward. And these are the formula for the backward propagation of the error towards the leaves. And we have done the same for EM. In this case, for computing the formulas, we have used the message passing by considering the equivalent graphical model to the circuit. And the interesting part is that since the circuit is a tree, the equivalent graphical model is a tree, so we can apply belief propagation and get correct result. So by applying belief propagation, we computed the values of the expectation by using this formula, where O minus is the inverse of O plus. So After this fast lecture, I want to conclude highlighting that this is an exciting field. There is still much to do because the objective is to be able to analyze bigger and bigger data sets, and especially nowadays, a large amount of relational data is available. For example, in the linked open data, cloud, the semantic web, knowledge graphs, Wikidata. This data must be exploited for learning, okay? But doing it is not easy because of the size of the data, of the distribution of the data, and so on. So probabilistic logic programming, inductive logic programming can be used to analyze this rich data, and to do so, however, we need to develop clever search strategies. We need to be able to learn programs with continuous variables, as we have seen in the first day. And also, we have to develop combination of deep learning with ILP, as Luke also yesterday showed, in order to exploit the possibility of deep learning to analyze continuous data with the ability of probabilistic inductive logic programming to perform sound inference even in the presence of uncertainty. So with this, I thank you very much for listening, and if you have any question, I will be pleased to answer.